All right, so let's take a look at the warm-up. So our warm-up says find x1 and x2 such that the linear combination of these two vectors is 2, -3. This is the problem we've been doing basically since the beginning of the semester. But now, once again, it means something different. We talked about yesterday in terms of coordinates. We're really finding the coordinates in terms of a new basis for 2, -3. So once again, same problem, different perspective again. So I have to find the x1 and the x2. So I'm going to throw this thing into a augmented system. So I'll have 1, 1, 2, 1 augmented with 2, -3. I'll do a little row reduction. This 1, 1, 2, 0, 1, 7. That's my forward process. Now I'll do my backwards process. 1, 0, and -5. All right, how's that look? So far, so good? Okay, so that tells me if I rewrite that now into a system form, this tells me that x1 equals -5 and x2 equals 7. So that's finding the right x1, x2 values, really answering the question for the warm-up. But once again, looking at this from a different perspective, if I said that we have a set of vectors, 1, 2, and 1, 1, I could ask, is that a basis for R2? Is this a basis for R2? It is a basis, and how do I know? How can I tell?
They're not scalars, and it forms a square matrix.
Absolutely. So they're not both multiples of each other. What does that tell us specifically?
That they're independent.
Absolutely. So I have two vectors that are not multiples. That tells me that they are linearly independent, which is one of the criteria for a basis. The other criteria is they have to be onto. It has to span all of R2. And we know that because square matrix. A square matrix. Once again, there's lots of ways to justify this. And I could see I only need 2 linearly independent vectors to span R2, so I have 2, so that will work. I could put that into a little matrix. In fact, I kind of did that. If I just look at this piece right here, this is just reducing just the matrix piece. I could say there's a pivot position for every row, which tells me it's onto the space. So all those ways I can kind of justify that this thing is onto. So it's a square matrix, which essentially tells me I have enough vectors and they're linearly dependent. So this together implies that it's onto. So I have linearly independent vectors that span the space. It's a basis. Is a basis for R2. Now that we have a basis, we can talk about different elements in our vector space in terms of the basis. So a very familiar basis, I'll call it B2 for R2, is 1, 0, and 0, 1. This is the standard basis. And so when I talk about vectors in R2, any random vector like this vector, 2, 3, I always talk about that in terms of the basis. So here's my vector. I'm going to call it V. V, in terms of my standard basis, B2, if I write out the coordinates in terms of that standard basis, I get 2, -3. Because 2 times this vector plus -3 times this vector gets me to this position. Right? So these are basically the directions in terms of the basis. Now this, of course, is the same as the vector. Right? But that's only because we're using the standard basis. But now I have a new basis. I said that this is also a basis. So this point, 2, -3, 1, 2, -3 down here, in terms of my regular basis, my standard basis, I go over 2, I go down 3, that's how I get there. But now once again I have a new basis that's 1 over 2 up. Here's one of my basis vectors. And 1, 1. So 1, 1 here. And so how do I use those vectors to get this position? Well, apparently I take -5 of these like this, and 7 of these. And that should get me to this point. So these are essentially the directions to this point in terms of these basis vectors. And so I would write that as, or express that concept as V, the coordinates of V, the square bracket, say I'm using coordinates, in terms of my basis B, not B2 this time, would be equal to -5, 7. Okay, so points, coordinates, directions to vectors in a vector space are really in terms of a specific basis. And since there are many bases, we should really specify. Aren't you mad at all your high school teachers? I told you about points. See, they should have been specifying the basis, right? Okay. All right, any questions so far? All right, so that's the warm-up. Plan for today is to continue on coordinate systems. So we kind of laid the foundation here in 2.9. Now we want to build on that in 4.4. So given a basis and a vector, we want to be able to find the coordinates just like we did. So we're going to practice that a little more. Also, given a basis, we want to be able to kind of transition one to the other. And we want to see how this might be a useful thing. And then in class, we should have a quiz on some of the concepts from Chapter 2. I have heard some concern about the quiz. I mean, we just finished the exam, moving really fast. Unfortunately, that's just the nature of this class, right? It's a summer class, it's condensed. So I'm concerned that by not having quizzes regularly, it just gets us a little behind, right? It doesn't let us prepare enough for the next exam coming forward. All right. Okay. So any questions before we launch into the lesson? Homework or from the exam or any lingering questions? Yep. Next exam, let's see. I think we have a little time here. I've modified our home page for Canvas a little bit to include some of the other pages. They revamped the Canvas interface a little bit beginning of summer, the way they manage pages. So, let's see here. So now I just kind of listed the pages on the front here. So today we are covering 4.4. Looks like we have 2 weeks from today is the second midterm. That gives us a week to finish up Chapter 6 and prepare for the final. Any other questions? So a couple people did the Gauss home or extra credit. I encourage you to do those extra credits. A nice little boost to your grade at the end of the semester. Any other questions? Okay, so from the warm-up we saw that given some basis, and we're going to write it all general here, because it might not be for R2, it might be for a bigger space, we might have more basis vectors. So given a basis, solving this thing, where this is a matrix, gives us the B coordinates of V, right? The coordinates to some element of the vector space in terms of the basis. And then we kind of have the expression to summarize that, the mathy equation that means that. So it's matrix times those coordinates equals standard coordinates. Now that might look a little, right, with a P sub B kind of thing. But to kind of understand what that means, let's just zip back up to the warm-up here. And we went through this process, and we were all done. We found the x1 and x2 that made this thing true. But of course, this vector equation is the same thing as a matrix equation. It's the same thing as 1, 2, 1, 1 times our x vector equals 2, negative 3. we solve this thing, we figured out that this was negative 5, 7. So this is just the matrix equation that we really solved. And if we look at that thing, we can kind of think about the parts. We said when everything was said and done, these were the new coordinates. These were the coordinates of our vector in terms of the new basis. All right, so if I grab this thing, bring it down here to our fancy expression. We said this piece here was just our vector in terms of the new basis. And the thing we started with here, well, that was just our vector in terms of our standard basis. And so this must be that special matrix that takes us back and forth here. And how did I get this matrix? Well, really, it's columns are my basis vectors. Any questions about that? Oh, that doesn't seem very useful so far, right? It's like, okay, well, I don't really have to write in a matrix equation. I just did it in terms of a vector equation. So, what's the advantage of me rewriting this thing in terms of a matrix equation? Well, one kind of advantage is that when we think about it also in terms of a transformation, hitting these coordinates with this matrix transforms it into our standard coordinates. But then, if we multiply our standard coordinates by the inverse matrix, that should transform them to our other coordinates. So when we think about it in terms of a matrix, then we can bring in the idea of an inverse matrix and kind of go back and forth. Or can we? I mean, it's easy enough to write this. And this is often the trap when you get into matrices and inverse matrices. It's easy enough to write that. Well, sure, if P times this thing equals this other thing, I can just do P inverse to get back. But anytime we write that, we have to ask ourselves a question. What's the question?
Is P invertible?
Is P invertible? Absolutely. Is there a P inverse? I mean, really, we always have to ask that question. I mean, even if we're doing something like 2x times y equals 10. I say solve this thing for x. We all go like this, 10 divided by 2x. But there should be a, wait a second, right? Is there always an inverse thing? Well, can I always divide by 2x? Not if x is 0. So I've thrown out some cases kind of automatically, mentally. I've eliminated the case where x equals 0. But we have to think about that process as we go. And here we have to be more explicit about that. Is there really an inverse? Well, luckily, there is an inverse. All right, so they have Theorem 8 from the text. Theorem 8, which basically says that a coordinate mapping, in other words, having some vector and being able to map it to its coordinates, if we can do that, then this is a one-to-one linear transformation from the vector space onto Rn. That's what the fancy theorem says. It says if you do this, if you can take a vector and map it to its coordinates, right? And here they're kind of being general about this vector idea, this vector space. Remember, these don't have to be the vectors that we're used to. This isn't us transforming 2, 3 to some other coordinates. This could be, as we'll see later, taking the vector space that all polynomials, like we did the other day. We said that the set of all second-degree polynomials is a vector space. Well, now I should be able to take those and somehow get coordinates for them. And if I can do that, then there's really no difference. And it's a one-to-one linear transformation from that set of polynomials, that space of polynomials, to R whatever the list of coordinates is. Now, normally you read through the section, you get to that theorem, and you say, oh, That's wonderful. One linear transformation be under I. But hopefully we can see why that's important. The reason they have that big theorem there is, because, okay, if that transformation is one-to-one, and it's linear, and it's onto, what does that tell us about the transformation? Does that answer our question? It does. Right? If it's linear, if it's one-to-one and onto, then it's invertible. So now we know that there always is that inverse matrix. So it's a theorem that's really telling us that, oh yeah, all this stuff says there does exist the inverse matrix. Okay, any questions about that? Okay, so let's look at kind of a little application here. Application in image processing, sort of. All right, we're starting with the vector v1, which is 1, 1. And so I can really think about that as the vector being the same thing as its coordinates in the standard basis. Right, if I talk about 1, 1, I'm talking about this point right here. And if I find its coordinates in the standard basis, it's 1, 1. We really don't distinguish between the coordinates and the vectors when we're using that standard basis. But what would the coordinates 1, 1, yield or look like if we were using a different basis? If we were using the basis 1, 1, negative 1, 1. In other words, if 1, 1 were the coordinates of some vector in this basis, what would this vector look like in the standard basis? So how would I find that? How do I go from these coordinates to these coordinates? I'll give you a second to think about it and chat about it and try to compute it. Look back at that last equation we looked at. So if you're stuck, make sure you ask, raise your hand, or how do I get started? So, let's grab it. Just zip this thing back here real quick. Grab these two things. We got those two things to help us, right? This was a matrix. This matrix times the coordinates in this basis gave us the coordinates in the standard basis. That's what we're trying to do. Trying to go from this basis, what does it look like in the standard basis? Which equation that we use? This one or this one? So what all these weird symbols mean? What is P sub B? Is it a vector, a matrix, a number? Okay, that one's going to be a matrix. And it's a matrix. We take this matrix times this. This will be a list of points, so it's going to look like a vector. It should give us a new one. And so we get this matrix by using these as the columns. Our basis vectors and columns. So, so for a warm-up, we said x1, x2 will be the coordinates of this thing in terms of these bases. These are the directions to get to here in terms of these bases. So we got our answer of -5/7. Go -5 in this direction, then go 7 in this direction. That's how you get to here. So it's like these are the directions of the streets. And these are how many blocks to go here.
No.
Yeah?
So we call these two values, like 3 blocks, 5 blocks. These are going to be the coordinates of this vector. Now, I can rewrite this as a matrix equation too, where it's this matrix, first column and second column, times these things, my coordinates basis, and the result will be this thing, which are coordinates in the standard basis. So this matrix, in this case, yep. So I could take this matrix times -5 seconds and get to this. So this thing is the piece of the matrix that we need to get by using the column.
All right, so let's take a look now. So we have our two equations here. Once again, this P here, this is a matrix that contains our basis vectors. And then we're going to have our coordinates in terms of those basis vectors. And if we take that product, it should give us the coordinates in terms of the standard vector. So in this case, we'll have 1, -1, 1, 1 times 1, 1 times our coordinates in that basis. And they should give us the coordinates in our standard basis. And so if I take this product, I get, well, before we actually do the multiplication here, let's think about what we expect as a result. Okay? So it's kind of like this. Here is my two basis vectors, this one, my standard basis. Now if I go 1 in this direction, 1 in this direction, I get to here. So this is representing the coordinate 1, 1 in the standard basis. Right? It tells me how to get to some point. But now I have a new set of basis vectors. I have 1, 1, which is this vector, and I have -1, 1, which is this vector. These are my new directions I can travel with. And so if I go 1 in this direction and 1 in this direction, where am I going to end up? Oh, somewhere in this area, right? Okay. So whatever this vector is, that's going to represent 1, 1 in terms of this basis. Okay? So then I do the product here. And I can take 1 times 1 is 1, -1 times 1 is -1. When I add them, I get 0. And when I finish the multiplication, I get 2 in the denominator. And so 0, 2, that is right here, so that kind of makes sense to me visually. Okay? So it's like if you're talking about these two directions, well then 1, 1 means this. If you're talking about these directions, then 1, 1 means this. Okay? Questions? And so we can think about changing the basis as changing the way R2 looks. It's changing the picture, it's changing the plane. It's stretching or rotating or shifting the world that we live in. Right? I should have another matrix video for this, right? That's really what's going on here. It's kind of like you took this thing, we went, and so all the points in here we can describe in terms of the standard basis, or we can describe all the points in here in terms of this other basis. But they would just mean different things. 1, 1 in this world means this, and that's changed over here, it means something different. Okay? So it's just like those transformations we did in chapter 1, where we did rotations and shifting and shears and reflections. We can think of all those as transforming, shifting, moving points, or we could think about those as looking at points in terms of a different basis. Okay? All right, questions about that? Okay, so with that in mind, I'm going to talk real quickly about parametric equations. How many people have worked with parametric equations before? People have seen parametric equations. How many people have had Calc 3? You guys gotten to parametric equations yet? So I got a handful here. Parametric equations are just a different way to describe equations. Normally if I want to plot parabola like that, it would be f of x equals x squared. You give me an x value, I tell you a y value, and together we get a point here, 1, 2, the x and the y value. Well, a parametric equation is just us traveling along that curve at different times. So at some time I'm here, sometime I'm here, sometime I'm here. I'm traveling along that curve. So what I do is I make a new function that's a function of time. And when you tell me the time, I will tell you what point we're at. I will tell you an x value that depends on that time and a y value that depends on that time. So as an example, I could have r of t equals, and sometimes I write them with parentheses, sometimes I write them in vector form like this, sometimes I write them like this. Lots of different ways. It's just a list of 2 values here. When I write them like this, and I put in an equation t comma t squared, you think, well, when t is 1, I would get 1, 1 as a point. 1, 1 as a point. When t is 2 at time 2, I would get 2, 4 as a point. 2, 4. And so for every different time, I'll get a different point. And it turns out that this specific parametric equation also describes that parabola. Okay, so why are we suddenly jumping to Calc 3 parametric equation kind of stuff? Because these parametric equations, for any given time, give us a point. They just give us a point. They give us some coordinates, actually, in terms of standard basis. So if we want, we can shift these things around using our matrix ideas. Okay, so for instance, oh, thank you. There we go. So I have my parametric equation here, right? It's just like a regular function. And I can plot it like a function. Instead of using plot, I use parametric plot. Instead of giving a range of x values, I give it a range of parameter values, t. So that's what I've done here. And there is my picture, my parabola. Now the idea is because the output of r of t is just a collection of points, if I want to think about those points in terms of a new basis, all I would have to do is take those points, take those points like this, and move them. So let's see, let's go like this. Like this. Now, what did I do here? All I'm doing is thinking about these points in terms of a different basis. Normally, I think about my points in terms of 1 and 1. But now I'm using a new basis, 1 and negative 1. And so if you said, go over to 1, 1, in terms of the standard basis, that would be 1, 1. But now I'm thinking about in terms of my new basis, 1 and 1. So if you said, go to the point 1, 1, I'd go 1 in this direction and 1 in this direction, one of my other basis direction. And if you said, go to the point 1, 3, that's 1 over and 3 up. So my scale's off here. It's like 1 over, it's 3 up in terms of the regular basis. But in terms of my new basis, that would be maybe 1, 3 would be 1 over and 3 in the direction of the other basis, down now. Okay, so by casting my problem in terms of this new basis, I've changed the space. And we could check out what other bases do. So now instead of 1, 0, and 0, 1, I have a different basis. I have this one, 1, 0, and now I have 1, 1 up here. It's kind of like I've taken my coordinate system like this, and I'm just skewing it like this. And so all the different points have to also shift accordingly as I look at it in this new world here. Okay. So linear algebra is going to give us a way to manipulate all these functions that we work with when we think about them in terms of parametric equations. Okay. Once again, it's not a new idea. It's the same thing we talked about when we talked about transforming transformations. A transformation you can think of as a transformation or as just looking at things in terms of a new basis. Okay. Questions about that? Okay. All right, but it's not just important for that reason. It's not just important because we can move and manipulate things. Another reason it's important because it allows us to think about other vector spaces in terms of spaces we're comfortable with. I'm very comfortable in R2. I'm very comfortable in R3. But when I cast things in terms of coordinates, everything looks like R2 or R3 or R4 depending on their size. Something abstract can look just like R2. So an example, for instance. We've kind of looked at an example like this before. If I say P sub 3, this is the set of all polynomials of degree less than or equal to 3. Third degree polynomials, cubics, or less. So this would be an example of a cubic. This would also be an example of something in that space. Doesn't have an x cubed term, but it's x cubed or less. But now I can say that I can create a basis for this vector space. Right, I have vectors here, 1, 2, 3, 4. 3 elements of my vector space. They don't look like vectors, but they are vectors because they're elements of my space. And I argue that I can take a linear combination of these things and get to any element in the space. I mean, that's really how our polynomials are defined, as a linear combination of these things. So I have to ask a couple questions. One, is that set of elements, set of vectors, is it onto? Well, sure, I can kind of look at it and say, yes, I can get to anything in this space. Right, if I just add up some multiple of these. That's once again how polynomials are defined. Is it linearly independent? Well, is there any combination of these 3 that will get me x cubed? No, right? When I add these things together, I don't change their powers. Is there any combination of these 3 that get me x squared? They don't. I can make the same argument for all of those. So they are linearly independent. So this really is a basis for this space. So now I have an element in my space. I'm going to call it P. So the P vector in this case is 1, negative x plus 3x squared minus x cubed. But in terms of this basis, I can find the coordinates of P with respect to my basis. It's the amount of all those directions I'm taking. So if I need to get to this thing, how many 1s do I need? How many 1s am I going to use to make this polynomial P? Just 1. How many x's do I need? Negative 1. How many x squareds do I need? 3. How many x cubes do I need? Negative 1. So this right here, these are the coordinates to this vector. Now, just like in R2, we really don't distinguish between the point and the vector, right? Because there's only one point, there's only one coordinate for each vector. We know that because of that transformation between elements to coordinates. So if I know that, if I know for every polynomial, every vector in my vector space, there is only one way to represent it like this, they're interchangeable. I don't have to think about this anymore, I can just think about this. They both describe the element uniquely. Okay? So now, I can totally ignore all this x squared, x cubed. I can just think of this as this vector, which means I can add it to other vectors. Right? And I don't have to go back and add the 2 polynomials. I can just add the 2 vectors. And it's basically the same as adding the polynomials. So it's a very important relationship between the elements of the vector and their coordinates. It's a special mapping. It's linear, it's one-to-one, and it's onto. In fact, we have a special name for it. We call them isomorphisms. Because it's like you're changing things, but you're not. You're preserving everything. We've taken all those ugly polynomials, mapped them all to vectors in a very special way, so that each one only has one relationship. And so now we can just say, okay, everything we do here is essentially the same. These 2 spaces are indistinguishable. For every action we can take on the coordinates, there's a similar action we could have taken on the elements if we wanted to. So we can't almost distinguish between the 2 spaces. Now, why is that so important? It allows us to talk about polynomials in vector terms. vector terms. So here are some things we might think about for vectors that now we can somehow relate to polynomials. What is the length of a vector? Have you ever asked how long is this polynomial? Well, we can talk about how long the polynomial is. We can have a relationship that talks about the length, and that's going to have a meaning somewhere. Okay? We can talk about polynomials being bigger or smaller in terms of their length. And once again, that has an important meaning, whereas before we couldn't. We can talk about the closeness of vectors. If you have three vectors, you can say, oh, these two are closer than the other one. Couldn't do that before with polynomials, but now we have a way to talk about that. And that idea of closeness is really going to help us do optimization. Okay? Not only can we solve a lot of problems with vectors in linear algebra, but it turns out we can approximate solutions also. We might not be able to find a vector that specifically solves this one. Remember, sometimes there's no solutions. But later we're going to learn about a way to find a vector that's the closest possible thing to a solution. It's the best approximation. And now we can take all those ideas, once again, and translate them to polynomials. I can find out what polynomial is closest to this solution that I want by thinking about it in terms of vectors. So this is really the power of thinking about it as an isomorphism, as the fact that this vector space, I can transform it into its coordinates. I can transform it into something in R3 or 4 or 5, and just work with the R2, 3, 4, 5 thing, just like I'm working with the polynomials. Okay, any questions about that? The problem is we're talking about all the things you can do, but we don't know how to do them yet. So now we have to find a way to talk about the length and closeness and optimization, and then we'll be able to see what that looks like in terms of polynomials. So that's what like chapter 5 is about talking about some of these ideas. Okay. Any last questions before the quiz? All right, no notes, closed book, closed notes. You can use your calculator to check your answers if you want, but I need to show the work. Alright, so just the front page here. First question is very similar to some that were on the exam. There is a calculate the inverse, so make sure you show me the steps for that. If that's using the definition, then show me the definition. And some true and false. Some other questions. Make sure if you have any questions, let something stated you ask.